Right, this is going to be a video about the laws of thermodynamics, which is chapter 18 in your textbook. We have already covered the zeroth law, so I'm not going to go through that. In fact, this is the same picture that we had in chapter 16. So now we're going to get to the first law. The first law is basically the conservation of energy. So the change in internal energy is related to the heat and the work. So here's our change in internal energy, and we take the amount of heat, which we saw earlier in the chapter, minus the work. And the signs on Q and W are very important. So if the system gains heat, meaning heat's coming into the system, then Q is positive. If the system is losing heat, then Q is negative. So if it's gaining heat, heat coming in, it's positive. If it's losing heat, then Q is negative. Now, if work is being done by the system on the surroundings, then the work is positive. But if work is being done on the system, then the work is negative. And you're probably going to need to be referring back to that chart as you do these problems. So the internal temperature of a system depends only on its temperature. The work done and the heat added depend on the details of the process involved, meaning heat and work are going to depend on the path, but the internal energy only depends on the temperature. And the temperature is a direct indicator of the internal energy. So if the temperature increases, usually the internal energy increases, and if the temperature decreases, then the internal energy decreases. So those are telling temperature is an indicator of that internal energy. So here we have an example. We have a swimmer that does 6.7 times 10 to the 5th joules of work and expels 4.1 times 10 to the 5th joules of heat during the workout. And this is going to be like the example that you have to do where you have to use, it's called two conventions. So our equation that we're going to be using is delta U is equal to Q minus W. Alright, so the first thing is our work, and it says they're doing 6.7 times 10 to the 5th joules of work. So if we are doing the work, then the work is going to be positive. So I'm going to put a little positive here. And they're expelling 4.1 times 10 to the 5th joules of heat. So that means the heat's leaving, so the heat's going to be a negative. So I'm going to take my Q, which is negative 4.1 times 10 to the 5th, and then I'm going to be subtracting my work, which is 6.7 times 10 to the 5th. So I'm going to negative minus this number. Basically means I'm going to add those together. And 1 after the decimal gets me 1 after the decimal, so negative 10.8 times 10 to the 5th joules. And you can see why those signs are very important, because it's going to make a difference of what kind of number you get. Alright, so we're going to assume all processes are in equilibrium and they're all reversible. And in order for them to be reversible, it has to be possible to return to both the system and its surroundings to exactly the same states that they were in before the process began. Alright, so we are going to be looking at a piston here, like an engine. So in the first one, the gas is compressed. So the piston's going to move down, it's going to compress the gas. The temperature is held constant, which means this is what's called an isothermal process. And heat is going to be leaving the gas. Then next, that piston is going to move up, the gas is going to expand, heat is going to be drawn in from the reservoir, and the gas in the reservoir are going to return to their initial states. So that's going to be an example of a reversible one, because we can see they both return back to their original states. Work is done by an expanding gas at constant pressure. And if we want to find the equation to find the work, then it's work equals pressure, our constant pressure, times our change in volume. And the one on your assignment, 1815, is going to be using this equation. Okay, if the volume stays the same, then that means no work is done, because if it's P delta V and delta V is constant, then the work is 0. So if you have constant volume, no work is done. Work is the area underneath the curve, as we've seen before. And in order to find the work, if we have constant temperature, we're going to do N, which is our number of moles, times R, our ideal gas law constant, the 8.314, times our temperature in Kelvin, and then ln of the final volume divided by the initial volume. So there's another way for us to find the work when the temperature is constant. An adiabatic process is one in which no heat flows into or out of the system. And an adiabatic pressure times volume curve is similar to the isothermal one that we saw before, but it's going to be steeper. And to ensure that a process is adiabatic, we must insulate the system, because that's going to help us to make sure there's no heat coming into or out of the system. Another way, besides insulating it, to make sure that an adiabatic process occurs is to change the volume very quickly. In that case, it doesn't have time for heat to flow in or out of the system. Now in this case, we can see that we have this plunger. It's going to move down in here. There's a piece of paper. So this is at room temperature. I'm going to squeeze it down very quickly. What that's going to do is that's going to create a high temperature environment in here, and that's going to cause the paper to burst into flames. So these are the different types of processes, and the problem on your assignment is called dealing with pistons. It's going to be looking at several of these kinds of relationships. So at constant pressure, work is P delta V. At constant volume, then we know there's no change in volume, so the work is 0. If it's isothermal, that means that we're at a constant temperature. So in that case, work is equal to Q, and delta U is 0. And if it's adiabatic and there's no heat flow, then if there's no heat flow, that means there's no Q, so the work is equal to your negative delta U. All right, so in this case, I have a reversible process, and this is A, this is B, and this is C. So in the first process, to go from A to B, it tells me the amount of heat that's associated with this. And this is actually, here's our pressure, and here's our volume. Now, to figure out our work, we have to do, since we have a constant pressure, we're going to do P delta V. Now, if my delta V is 0, then that means my work is 0, because work is P delta V. So if my work is 0, then I can find delta U, because in order to find delta U, I always do Q minus W. So if Q is negative 53.0 and I subtract 0, I get negative 53.0 joules. Okay, now in the next case, to go from B to C, I do have a change in volume, and I know both Q and W. So in this case, I'm going to be taking my Q, which is negative 32.5, going to be subtracting my negative 130 to find my delta U. And when I do that, I'm going to get negative 195 joules. Now, in order for me, that's from B to C. Now, to go from C to A, I'm returning back to the original state, which means that the amount of energy that was expelled is going to be all returned back to the original state. So if I take 195 and the 53, I'm going to have to be adding those together and change the sign. And when I do that, I'm going to get 248 joules. And now I have to find Q. So in this case, I take Q minus W, and that's equal to my energy. So in order to find Q, I basically add this to the other side. And when I do that, I'm going to get 331 joules. So that's kind of looking at those different processes. Specific heats for ideal gases have to be either constant volume or constant pressure because they're going to be slightly different. So for a constant volume process, we can see they put a little V here. So the heat for constant volume is N, your number of moles, times your specific heat at constant volume, times your temperature change. And if they're at constant pressure, then Q at constant pressure is going to be N, your number of moles, times your specific heat at constant pressure, times your change in temperature. And we can calculate both of those using the first law of thermodynamics. If they're at constant volume, then we do 3/2 times R. If we are at constant pressure, then we do 5/2 times R, which means the difference between CP and CV is R. And we're going to be using these in our next problem. So although this calculation was done for ideal monatomic gases, it works well for fairly real gases as well. We said the difference is supposed to be R, so we can see all of these are 1R or about 1R, and this is also about 1R. In this case, we want to know how much work is done when 49 moles of a monatomic gas expands from 0.75 to 1.9 meters cubed at a constant pressure of 210. So in order to find work, we're going to use P delta V because we're at constant pressure. And I'm going to have my pressure in pascals. And then the change in volume is 1.9 minus 0.75. So I'm going to subtract 1.9 minus 0.75 and take it times 210. And I'm going to get 2.4 times 10 to the 5th joules. Now part B says what is the initial and final temperature of the gas. So in this case I'm going to be using my ideal gas law. So the pressure that we had constant was 210,000. My initial volume was 0.75. N was 49 moles. R is 8.314, and then I can find T. I'm going to do the same thing for my other volume, which was 1.9. And my first temperature, if I take this times this divided by those two, I should get 390 Kelvin. And then if I take that divided by those, my temperature is going to be 980 Kelvin. So then C wants to know what's the change in energy of the gas. So in order to find my change in energy, I'm going to use my equation. And N was 49, R is 8.314, and then my temperature difference was 980 minus 390. And I got 3.6 times 10 to the 5th joules. And D wants to know how much heat is absorbed. So delta U is Q minus W. And for part 1, I got 2.4 times 10 to the 5th was my Q. And then my work okay, so delta U I just found 3.6 times 10 to the 5th. Trying to find Q, and my work I found in part A, which was 2.4 times 10 to the 5th. So I'm basically going to be adding those together to find Q. And I got 6.0 times 10 to the 5th joules. Okay, this is another example. In this case, I have 535 joules of heat, and it's absorbed by 45 moles of a monatomic ideal gas at constant volume. And they want to know what's the change in temperature. So in this case, if I'm at constant volume, oh, and this is like 18.24 and 18.36 on your assignment. If I'm at constant volume, then work is P delta V, which means work is going to be 0. And they gave me that I have 535 joules of heat. So I have 535 joules of heat absorbed, so that's a positive, minus 0, which means my change in energy is 535. And I'm going to then find my change in volume, and since this is at, or my change in temperature, and since this is at constant volume, 3/2 nR delta T. N is 45, R is 8.314, and I find delta T, and I know U, change in U, is the 535 that I had before. So I can find my change in temperature by taking the 535 divided by that amount, and I got 0.95 Kelvin. Now I'm supposed to repeat this calculation, but this time at constant pressure. So at constant pressure, then I know that Q at constant pressure is 5/2 nR delta T. So Q was the 535 times 5/2, 45 times R, 8.314, and then I can find delta T. .57. But I better check that. Kelvin. Now in this case, since my work was 0, Q is 535, so that's why here I use delta U, but delta U is the same thing as Q at constant volume. In this case, since my volume was constant. Okay, the second law of thermodynamics, so we had the 0th law, then we covered the first law, which was conservation of energy. The second law says that when objects of different temperatures are brought into thermal contact, then heat always results a flow from the high temperature to the low temperature, meaning it can't go in reverse. So the object at higher temperature always gives it to the object at a lower temperature. So a heat engine is a device that converts heat into work. An example would be a steam engine. So the fuel heats the water, the vapor expands, it does work against the piston, and then the vapor condenses back into water and the cycle repeats itself. And all heat engines have a high temperature reservoir and a cold temperature reservoir and a cyclical engine. So in this case, here's my hot temperature reservoir, and the amount of heat that is supplied from the hot reservoir, some of it appears as work, and the rest of it, the cold, is given off as waste to the cold reservoir. So in order to find the work, The work is the difference between the hot reservoir and the cold reservoir. And the efficiency is the fraction of the heat that's supplied as work. So I'm going to take my work and divide by Q of the hot. In other words, the heat of the hot reservoir. And I can also write the efficiency. So I said it was work divided by Q hot. Work is Q hot minus Q cold over Q hot. So I could break this up. This would be 1 minus Q cold over Q hot. And the efficiency does not have a unit on it. So in order for the engine to run, there has to be a temperature difference between the hot reservoir and the cold reservoir. Otherwise, there's not going to be any heat that's transferred. Okay, so in this case, we have to find the efficiency of an engine if it exhausts 870 joules of heat while doing 340 joules of work. So in order for me to find my efficiency, I have to take work divided by Q hot. So right now, I know that Q hot minus Q cold is going to be my work. And it says I have 340 joules of work, and that my Q of my hot is what I'm trying to find, and the Q of my cold is the 870. So I'm going to be adding those together, and when I add those together, I'm going to get 1,210 joules. So now I can go ahead and find my efficiency by taking my work, which is 340, divided by Q of my hot, which is 1210. And that means when I divide those, I can find my efficiency, which is 0.28. And the example that you have is 18.46, which is going to be similar to this. A maximum efficiency heat engine is one in that it's reversible, and they are operating between the same two temperatures in order to have the same efficiency. So we can have two engines, they're both reversible. As long as they operate at the same two temperature environments, they're going to have the same efficiency. Now this is an ideal heat engine. No real engines are going to be completely reversible, meaning we can't take them back to the same set of conditions. And the efficiency depends on the two temperatures. And in order for those to be the same, we have to have the same ratio of the transferred heat. And to find the maximum efficiency, we can take 1 minus the cold temperature minus the hot temperature, divided by the hot temperature. And that's to find maximum efficiency. And the maximum work then it can do is the efficiency times Q of the hot. So this was my efficiency, and then I can take it times the hot reservoir. So at the same temperature, the efficiency is 0. That's because this is going to be 1, and 1 minus 1 would be 0. The smaller the ratio of the cold to the hot, the closer the efficiency will be to 1. And a heat pump is, we said from the second law, heat is transferred from the hot to the cold, and heat only flows backwards if work is done. Otherwise, it's not going to do it by itself. Refrigerators, air conditioners, and heat pumps all use work to transfer heat from a cold object to a hot object. So you can think about in your home, you take from your hot environment and you're expelling the heat outside to an even warmer environment. And in a refrigerator, you're exhausting the heat from the inside of the refrigerator to the outside. And that isn't going to happen. Like your refrigerator is colder, it's not going to expel, it's not going to go from cold to hot unless work is done. And obviously it's going to take electricity, that's where the work is coming from. So a refrigerator is a heat engine that runs backwards. So is an air conditioner. Heat's extracted from inside the refrigerator and then exhausted to the kitchen. And because there is work done, more heat is exhausted than is removed from the refrigerator. because some of that work that you're putting in there is being expelled out as well. So the idea that you could leave your refrigerator open and it would cool the room is not true. Your room would heat up because you're constantly putting more heat back out into the room than you are expelling from the food. And the coefficient of performance tells us how much heat is removed per the amount of work that we put in. So to find the coefficient of performance, we take the heat that's removed from the cold and divide it by the work that is done. And typical refrigerators have coefficient of performance values of 2 to 6. And the bigger your coefficient of performance, the better. An air conditioner operates like a refrigerator. Heat is extracted from your home, which is the cold temperature, and exhausted outdoors to the hot temperature. And exhausting within the house will result in the house being warmer, just as keeping the refrigerator door will result in the kitchen being warmer. So that's why we have to always exhaust it outside your home. And if you have a central air conditioner and you've ever been outside by your air conditioning unit that sits outside, you're going to be feeling heat that's being given off to the outside. And that's that heat that's expelled. A heat pump is the same thing as an air conditioner, except you can reverse the reservoirs, meaning it runs like an air conditioner in the summertime, but then you can flip a switch and it will run in reverse. And in that case, you can remove heat from the cold reservoir outside, and then you can exhaust it into the house in order to heat your home. And that's the same whether it's an air-to-air heat pump or whether you have a ground source heat pump. You're still taking it from a colder environment and putting it into the warmer environment, which is your home. All right, so we said that work is Q hot minus Q cold, or we could take Q hot, 1 minus Q cold divided by Q hot. So in this case, we also said that Q hot was 1 minus T cold over T hot. So in order to find the coefficient of performance for a heat pump, we said that it's Q hot divided by work. And there is no unit on your coefficient of performance. So in this case, the coefficient, this is an example, I have the coefficient of performance of 1.75, and the engine absorbs 3.45, this should be times 10 to the 4th, joules of heat from the cold reservoir. And we want to know the amount of work that's done. So Q cold is 3.45 times 10 to the 4th joules. And we're asked to find the work, and my coefficient of performance is 1.75. So 3.45 times 10 to the 4th divided by my work is going to be my coefficient of performance, which is 1.75. So in order for me to find my work, I'm going to have to take 3.45 times 10 to the 4th divided by my 1.75. 1.97 times 10 to the 4th joules. Alright, then we'll go on to the next part, and it says what's the temperature of the hot reservoir. And there is a mistake here. It's asking for the heat of the hot reservoir. And we know that work is Q hot minus Q cold. And we just found my work, 1.97 times 10 to the 4th. And we know that Q of the cold is 3.45 times 10 to the 4th. So in order for me to find Q of the hot, then I'm going to simply add those together. And I'm going to get 5.42 times 10 to the 4th. Alright, a reversible engine has the following relationship between the heat transferred and the reservoir temperature. So Q cold over Q hot is the same ratio as T cold over T hot. Or if I wanted to rewrite that, then Q of the cold over temperature of the cold is Q of the hot over the temperature of the hot. So we could use a ratio to solve for our temperatures. And this is the same, this relationship is the same for both reservoirs. Now entropy is delta S, and entropy is a measure of disorder. And in order to find that disorder, I'm going to take Q, which is my heat, divided by my temperature. And that, if we look back at the last slide, we have Q cold over T cold, and then we had Q hot over T hot. That was the entropy. So the heat transfer has to be reversible for this to hold true, and reversible processes result in no change in entropy. Irreversible processes will result in an increase in the entropy. The total entropy of the universe increases, its ability to do work decreases, and that's because in the universe it's an irreversible process, meaning it's not reversible. So the excess heat that's exhausted during an irreversible process can't be recovered. It's in a form that we can no longer use. And if it was, that would be a decrease in entropy, which is not possible. So the entropy of the universe is always increasing. Just like in your home, if you would leave it be and not do any work, the entropy is going to increase, the disorder. So we said entropy was a measure of disorder. And in this diagram, the end state is less ordered than the initial state, meaning more disorder, so more entropy, and the separation between the low and the high temperature areas have been lost. Now this is an example on entropy. It says, what's the change in entropy required to vaporize 1.85 kilograms of water into steam at 100 degrees? And the example that you have in your assignment says hot to cold is going to be like this entropy example. So I'm going to have to take my heat divided by my temperature change. Now I'm trying to vaporize something, so I'm going to have to go back and know that Q is my mass times my latent heat. My mass is 1.85, and the latent heat of vaporization in this case, because I'm going from water into steam, is going to be 22.6 times 10 to the 5th, and I looked that up in a chart on a previous chapter. And when I multiply those, I get 4.18 times 10 to the 6th joules. So that's going to be Q. And then I have to divide by my temperature, but it has to be in Kelvin, so 100 plus 273 is going to be 373 Kelvin. And when I divide those, that's going to give me my change in entropy. And that's going to be joules per Kelvin, because I have joules on the top and Kelvin on the bottom. Okay, so third law of thermodynamics says it's impossible to lower the temperature of an object to absolute zero in a finite number of steps, meaning I cannot reach absolute zero. So absolute zero can't be reached. Another way that the absolute zero is the lowest temperature that's possible, which is 0 Kelvin. We can approach it, but we can't ever get there. So we can't ever be reached. We can get close. And 2 times 10 to the minus 8th Kelvin has been achieved in a lab. So we can get close, but we can't ever get to absolute zero. The absolute zero can't be reached. And that is the end of chapter 18.